Hi, welcome back. Third video then on energy. I need to talk to you about how we measure energy changes. And I always say to my classes, wouldn't it be great if we had an energy meter? An energy meter to measure energy changes. There's no such thing. In the absence of an energy meter, then how do we measure energy changes? Well, what we do is we use what's called the specific heat capacity of water. Now, when I was younger, all my pupils would know the specific heat capacity of water. It was like me asking, what's the boiling point of water? 100 degrees. What's the specific heat capacity of water? 4.2 joules per gram per degree, sir. But nowadays, pupils don't know it. That general knowledge has been lost in the generations. So let's go back and have a look at what specific heat capacity actually is. Right, this is it. Learn. Both of these sentences represent heat capacity of water, specific heat capacity of water. So just follow it carefully and logically with me. To raise the temperature of 1,000 grams, a kilogram of water, by 1 degree Celsius will take an exact amount of energy, which is 4.184 joules of energy. The units clearly would be joules. Sorry, that's per gram. Let me say that again. Temperature to raise the temperature of 1 gram of water, that first sentence. This is the kilogram sentence. I'm sorry, I got them mixed up. So let's just start again. To raise the temperature of 1 gram of water by 1 degree will take 4.18 joules of energy, and there it's written 4.18. Capital J for joules, small g for grams, -1 means per gram, and degree Celsius per degree Celsius, 4.18 joules per gram per degree Celsius. Now, scaling that up to a kilogram, in physics textbooks, it tends to be written per kilogram. And I think the definition strictly should be per kilogram, because a kilogram is the SI unit. And therefore, in kilogram terms, this next sentence, learn that too. Learn them both, they're very similar. So, same sentence in kilograms reads, to raise the temperature of a kilogram of water by 1 degree Celsius. Now, 1 degree Celsius and 1 Kelvin are exactly the same size. So that is 1 degree Celsius or 1 Kelvin. It will take 4.18 kilojoules of energy. And therefore, in kilogram terms, the answer written is 4.184 kilojoules per Kelvin per gram, per kilogram. Let me say that again. 4.184 kilojoules per Kelvin per kilogram. NB at the bottom there. The size of a Kelvin is exactly the same size as 1 degree Celsius, so the temperature rise will be exactly the same. So when we talk about the temperature rise going up like 5 degrees Celsius, that's the same as saying it goes up 5 degrees Kelvin. Whether you've got a temperature rise in Kelvin or whether you've got a temperature rise in degrees Celsius is exactly the same. Don't let that confuse you. Having taught you what a specific heat capacity of water is, then to measure a temperature rise, we use this equation. And then we use this equation to scale up to a mole. So when we do a small scale experiment like I'm going to, we're going to find out what the energy change is in the experiment. I call it delta E, change in energy. Then that change in energy will be mass of the water times specific heat capacity of the water times the temperature rise of the water. And most of our solutions are nearly all water. So when we've got solutions, we just treat it as water and consequently, we work out here in red, I've annotated it, M is mass of the water or solutions, and that's going to be the same as the volume of solutions. Now that's my first experiment I'm going to do. I'm going to need that approximation. The volume of the solution is the mass of the water in that solution, because there's very little solute dissolved. The C is heat capacity of water. Whether I'm dealing in grams or kilograms, you need to be aware of what the right units are, and the right units are crucial in the calculations. And delta T is the temperature rise. We're going to measure in Celsius using our blue fill thermometers, and therefore that will be in degrees Celsius. And the temperature rise, whether it's Celsius or Kelvin, doesn't matter. And then that small scale experiment that I do will have to be scaled up to a mole. I think we're going to work on 1/10 of a mole, and then we're going to have to multiply by 10. We'll use this equation here. I'll come back to that, and I will do a calculation this video too to show you. So let's show you the apparatus for the practical. This is the practical. What we're going to do is we're going to react alkali with acid, hydrochloric acid, sodium hydroxide. Now we've made these a little bit stronger so that there's more dissolved acid and dissolved alkali in here. So when we get a reaction, the temperature rise will be a bit bigger. And to save time and save me faffing around, I've already measured 50 of alkali there, and I've measured 50 of acid there. 50 centimeters cubed. Now, I hope you know every 1 centimeter cubed of water weighs 1 gram or has a mass of 1 gram. And therefore 50 of water and 50 of this solution will be 50 grams of water in there. 50 grams of water in there, because these solutions are mainly water. So 50 grams and 50 grams makes 100 grams of water overall. We can use a thermometer to measure the temperature rise. So if I try and show you that again, I know it's not ideal, but that reads, believe it or not, that reads 19 degrees. 19 degrees. Blue fill thermometer is not so reliable, so don't bank on this. Absolutely, I mean the experiment is sound. Nothing wrong with the experiment, but the temperature, we're only after temperature rise, so it won't matter that much anyway. So we need to start with one chemical. This is the alkali. Put that in there. And this is a coffee cup. It's a coffee cup. Coffee cup made of polystyrene. And polystyrene is good at keeping heat in. We've put it in a beaker in order to give it a bit more insulation, and it gives it a bit of strength as I move it around. If I move this around, I sometimes rip it and break it. So in there, that is the alkali. Now, let me show you. Can you see don't know if you see the temperature in there. I hope you can see it's about 19 degrees. And now what I'm going to do is get the acid and react it. So acid, reacting it. 50 of alkali with 50 of acid. Stir it around, get it all to react. Show you that the temperature's gone up. 30 odd. Don't know if you see that. If I have a look at it and read it, ion head on, that is 31.5 degrees. 31.5 degrees. So if it started the temperature at 19 and now it's 31.5, that is an increase of 31.5 minus 19, which is 12.5 degrees. So this experiment gave a temperature rise of 12.5 degrees. Now, how do we work out a delta H numerical value with such an experiment? Well, let me show you on my PowerPoint. That experiment that I've just demonstrated, that experiment is a neutralisation. It's an acid-alkali reaction. That's the ideal apparatus we would use. Schools don't have that kind of apparatus. If your school does, count yourself lucky. My school doesn't have that kind of apparatus. We don't have a cork stopper. We do have glass stirrers. We don't have this setup. We don't use 2 coffee cups. We just use a beaker and a coffee cup. But that is better. Now, the reason we don't have the best equipment like that is exam questions want you to suggest an improvement. And the improvement here is 2 coffee cups are better insulating than 1 coffee cup. Putting a lid on it. I never had a lid on my demonstration. So my demonstration can be made better by having these modifications. And that's why we don't have the best apparatus here, because we want our pupils to know what the modifications are, because they ask about them in an exam. So our school setup are just coffee cups. And we give out coffee cups even without the lids. With a lid, the experiment would be better. We'd give them out without the lids so that putting a lid would be an improvement. So the calculation, what kind of calculation do we do? Well, 50 of 2 mole per litre hydrochloric acid is reacted with 50 of 2 mole per litre sodium hydroxide. So 50 of acid with 50 of alkali, that's what I did. The concentration were 2 mole per litre of both. Assume that the solutions are water, and then we can do the calculation. So M is mass of water. 50 and 50, mass is 100 grams, roughly, that's fine. C is 4.18. Change of temperature was 12.5 degrees. Now, I did this before the demonstration that I've just done, and with a previous year result from a pupil, I put that in and worked it out. So let's have a look what my last year pupil got when he actually did this experiment. 12.2 degrees. He got 12.2 degrees Celsius rise in temperature. So how do we do the calculation? Change in energy is mass is 100. If it's grams, then this number is 4.18 because it's whatever per gram. And then the answer will be joules. So 100 grams, each gram needs 4.18 joules to raise by 1 degree, but we've got a temperature rise of 12.2 degrees. So you multiply those together, and if you do that on your calculator, you get an answer of 5,099.6 joules. Now that is for that small scale experiment. We need to scale up to a mole. Number of moles of acid alkali. If you do the moles topic to do with concentrations, to work out number of moles, you have to take the volume in litres, 50 over 1,000, 50 over 1,000 times the concentration, which was 2. And that means the number of moles of acid was 1/10 of a mole, 0.1 moles. Number of moles of alkali, same calculation, was 0.1 moles. So we had 1/10 of a mole of acid, 1/10 of a mole of alkali, and together they would make 1/10 of a mole of water and sodium chloride. So how do we scale up? Well, we scale up by taking that answer delta E, dividing by 0.1, and that multiplies everything by 10. Dividing by 0.1 is the same as multiplying by 10. So on a scale where if we needed a mole of acid with a mole of alkali, then we'd have to multiply by 10 to get that answer, which is 50,996 joules. Now 50,996 joules is about 51 kilojoules. And the units, I want you to write them like that, kilojoules per mole. In fact, kilojoules per mole is the most common unit of energy in this topic because 1 joule is very tiny. So 1,000 joules, kilojoule, is what we normally measure in, and we always do per mole because it's however many moles are in the balanced equation. And that is the calculation, and you've got to be able to do calculations. Now, note about this calorimetry experiment. For neutralisation experiment, the final results are within 20% of the real answer. The real answer, the book answer, the scientific answer is 57 kilojoules. What did we get? We got 51. So we're out by 6 kilojoules. We're out by about, 12%. That's just doing it in my head roughly. The real answer is 57. And why is the real answer always 57 when an acid reacts with an alkali? Well, the acid provides the hydrogen ions. The alkali provides the hydroxide ions. Acid, alkali make water. It doesn't matter what your acid is and what your alkali is. The acid-alkali will always, ionic equation will always be that. And therefore, when a mole of hydrogen ions react with a mole of hydroxide ions, making water, they give out 57 kilojoules of energy per mole of water formed. And that is a famous value known by people, and it's famous for neutralisation experiments where acid and alkali react together. Now you can use the exact same setup for, say I had copper sulfate and I wanted to tip into that some solid zinc dust. Then you could use that and do the same thing and scale up. So that template where we work out the energy and then scale up can be used with other reactions such as displacement reactions. Now I don't know what context they're going to give you these in an exam, and therefore you've got to be able to deal with that template of whatever context they give you. You've got to use the specific heat capacity of water to work out the energy change in your experiment. You have to scale up to a mole to get per mole of reaction, etc. And then they ask you these kind of questions. Is it a good experiment? And I would say that the coffee cup, that is a good experiment. It's a good experiment because the heat energy changes inside and the coffee cup keeps the heat inside quite well. How can you improve it? Well, put a lid on it. Lid on it. Perhaps instead of a beaker, use another coffee cup as a better insulator. Insulator means it'll keep the heat energy in, and we want the heat energy to be kept in while we measure the temperature rise using a thermometer. Okay, 20 minutes, so I'm going to pause it there. And next, we're going to look at combustion, that's burning. We're going to look at, can we measure the energy change when things are burning? And I'm going to show you how we do that. And those experiments I'm about to show you are not going to be good. These are good experiments, but those are not good experiments. And we cannot do combustion experiments because coffee cups, in our combustion experiments, coffee cups would burn. And therefore, we need a different way of doing it. And the different way is that way. And I'll pick up from there. I'll pick up that next time.